In this video, I will share how to derive an expression for electric potential due to an electric dipole. There are two cases. One is what will be electric potential on axial line of electric dipole, and second will be on equatorial line. First of all, let us see how to derive electric potential on axial line of electric dipole. Suppose this is an electric dipole having charges minus q and plus q point charges. Suppose these are separated through distance L. So this line joining the two charges is nothing but the axial line where electric potential due to the dipole is to be calculated. Let us suppose here is point of observation. Let me call it point P, and first charge is placed at A, second charge at B. This is the center of electric dipole, and half of the length, if total is L, it will be L by 2, and second half will also be equal to L by 2. Suppose O is center of the dipole and distance of point of observation from center of dipole, suppose it is equal to R. Our question is what will be total electric potential at point P due to charge minus Q and due to charge plus Q, that is due to whole electric dipole. For that purpose, let me suppose electric potential at point P denoted by V with the subscript minus Q. Its value can be written as 1/4 pi epsilon naught minus Q divided by distance between minus Q and point of observation, because these distances are, and this one is L by 2, so in the denominator I can write R plus L by 2. Similarly, potential at P due to charge plus Q can be written as 1/4 pi epsilon naught. Here charge is to be plus Q divided by distance between source charge and the point of observation. Here distance will be R minus L by 2. I will write R minus L by 2. And total potential at point P will be algebraic sum of this potential and this potential, that is V due to minus Q plus V due to plus Q. Now both the values are known to us. We can put this value here, and simplifying we shall get Q upon 4 pi epsilon naught as common. Inside we shall be left with minus 1 upon R plus L by 2 plus 1 upon R minus L by 2. Now we have to solve this bracket by taking LCM. I can write R upon 4 pi epsilon naught. Inside the bracket it will come out to be R square minus L by 2 whole square. This is LCM of this thing. In the numerator I will get minus R minus L by 2 plus R plus L by 2. Now we have to simplify this mathematics and get the required answer for V. After simplification, we can write total potential at point P as equal to Q upon 4 pi epsilon naught. Within the bracket we are left with Q multiplied with L in the denominator R square minus L by 2 whole square. Now Q into L is nothing but electric dipole moment. So this product can be replaced by P. So total potential can be written as 1 upon 4 pi epsilon naught P divided by R square minus L by 2 whole square. So this is the required expression for total electric potential at a point P distant r from center of the dipole, where L represents length of the dipole. Now let us do a special case. Special case is that if point of observation lies far away from the dipole, means when L by 2 is very less than R, or when R is very greater in comparison to length of the dipole, then in this result L by 2 whole square can be neglected in comparison to R square, and we are left with V equal to 1 upon 4 pi epsilon naught P divided by R square. So this is the expression for electric potential due to electric dipole at a point P on its axial line. So by putting the values of R, we can calculate potential at any point P distant R from center of the dipole. That's all. Now let us calculate electric potential due to dipole at a point on its equatorial line. As done earlier, let us again consider the same electric dipole consisting of charges minus q and plus q located at A and at B. Suppose the length of the dipole is L. This is axial line of dipole, and right bisector of this axial line, length of the dipole, is nothing but equatorial line. On this equatorial line, let us suppose this is point of observation where electric potential is to be calculated. Again, let me divide the length into two parts. This part L by 2 and the second half of dipole L by 2. Suppose this distance is AP and distance of second is also AP, and let us suppose distance of point of observation from center of the dipole is R. We have to calculate potential due to both these and then add them up. Potential at P due to charge minus Q can be written as 1 upon 4 pi epsilon naught minus Q upon distance of point of observation from source charge. This distance is AP. Now the value of AP can be found by using Pythagoras theorem. So I can write 1 upon 4 pi epsilon naught minus Q divided by, what is AP? It will be perpendicular square plus base square under the root, that is R square plus L by 2 square whole under the root. Similarly, electric potential at point P due to second charge plus Q can be found to be equal to 1 upon 4 pi epsilon naught plus Q divided by, here distance is BP. As done earlier, BP will be also equal to R square plus L by 2 whole square under the root. So answer will be 1 upon 4 pi epsilon naught plus Q divided by R square plus L by 2 square under the root. So we have found answer for potential due to minus Q charge and potential due to charge plus Q. So the result total potential at point P will be V due to minus plus V due to plus Q. Potential is a scalar quantity, so its total is calculated by algebraic sum of two values of potential. By adding these two, I can write Q upon 4 pi epsilon naught under root R square plus L by 2 whole square taken as common. Inside, we shall be left with minus 1 plus 1. So it is clear the total potential will come out to be 0. So at any point on the equatorial line of electric dipole, net electric potential is always 0. That's all.